Okay, we stopped here last time. This is still chapter 19, talk about the tool technology. Last time, uh, we were talking about the tool life, and we make tool life analysis. Already finished this one. We stopped about the tool material. Tool material. What is the tool material? When you say tool material, it means that what is the material that we use to manufacturing the tool. This is the tool. This is a cutting tool, right? Please understand that a cutting tool must be harder than the workpiece material. Cutting tool must be rigid enough to cut the workpiece material. So what is the material to manufacturing the cutting tool? Before we talk about the material to manufacturing the cutting tool, we discuss first what is the properties, the tool material properties, or the properties that tool material should have to avoid tool failure or tool fracture. What is these properties? We have what we call is the toughness, wear resistance, and hot hardness. Three different or three important properties. Actually, toughness, when you say toughness, it means that ductility. In other word, we can say toughness is a ductility. And the opposite of the toughness is a brittleness. So toughness is the ability of the material to absorb energy and plastically deform it without fracture, avoid fracture failure. It means that material absorbs the energy, absorbs the impact. Material can be deformed to absorb this impact. This is the meaning of toughness. Toughness, in other word, means that ductility of the material. More ductile, more toughness. Less ductile is less toughness or higher brittleness. For example, if you have a very hard material, very hard material, meaning toughness is very low. This material, even it is very hard, toughness is very low and cannot withstand the impact or cannot absorb impact coming from cutting. Like glass, for example. Glass is very hard material. But when you try to impact the glass, glass will be broken because the toughness is very low. So toughness is very important. We need a higher toughness. And also at the same time, material should have higher wear resistance. Wear resistance means higher hardness because material here, the tool material here in a cutting always in contact with the chip, and it is very tough situation, and exposure to the wear, very high wear, then material must be wear resistant or higher hardness. So you can see that toughness and hardness are opposite to each other. If material have a higher hardness, meaning lower toughness. If material have a higher toughness, mean lower resistance or wear resistance or lower hardness. So what should be? What should be? Should be higher toughness or higher hardness? It should be compromised between toughness and hardness. Should be higher hardness and in somehow improve the toughness to keep that in a good toughness range. Otherwise, if it is very high hardness, if the material have very high hardness and very low toughness, material will be very brittle, and if material very brittle means that material also is not good, because if very brittle it will mean that material will not be able to absorb or to withstand the impact coming from the cutting, and then it will be broken or fraction will happen. So it's also not very good to be have material have very high hardness. Also, we have whatever we call is a hot hardness. Not hardness, but hot hardness. What is the hot hardness? Is the hot hardness is the ability to maintain a hardness at a higher temperature. Maintain hardness at higher temperature. Is it important? Yes, it is. This one is very important because actually in a cutting zone, temperature increase significantly. In a cutting zone, temperature here increase significantly up to 600, 700, 800 degrees Celsius. And sometimes more, depend on what is the cutting condition and the cutting speed. And if tool working at this kind of temperature, what happened to the hardness? Even at room temperature, you can see that this is at room temperature, right? For several material to be used to manufacturing tool like Plain carbon steel, high-speed steel, cobalt steel, cemented carbide, ceramic, all this material being used to manufacturing tool. At room temperature, you can see that not that very much big difference between the hardness for this kind of several tool. But what happened when temperature increase? So you can see that temperature increase. You can see plain carbon steel, high-speed steel, cast cobalt alloy, cemented carbide, ceramic. You can see that what is the behavior of the material. Is this material able to maintain a hardness at higher temperature? This is whatever we call is a hot hardness. So hot hardness is very important. Not only hardness, but hot hardness, right? Actually, this is a history of the tool manufacturing or tool material manufacturing. This is the history. You can see here, you can see this is figure describes the history of the tool material manufacturing. Initially they start with a plain carbon steel material, manufacturing tool made of plain carbon steel. And you can see that what is the problem with the plain carbon steel. This is the plain carbon steel. What is the problem? The problem is plain carbon steel at room temperature is okay, but when temperature increase in the cutting zone, then you see that hardness decline, severely decline, tool become really soft. This means that the tool flow, material plastic flow will happen, material plastic deform, cutting angle deform. This one leading to damage of the tool. Tool totally will not be able to withstand the cutting at the higher temperature, so it is not really good. And later on, they improve manufacturing whatever we call high-speed steel. So next generation of the tool is the high-speed steel. This is a high-speed steel. It is, they call it high-speed steel because it is compared with the plain carbon steel, it is a higher speed. So they call at that time when they manufacturing this kind of tool material, they call it as a high-speed steel. It show improvement. It show improvement. The hardness at the room temperature is higher, and even at elevated temperature. For example, if you look to temperature at 800, it means that 800 is here. So 800 degree plain carbon steel cannot work at all, but high speed steel is still better, much better, show better improvement in a cutting. So you can see that it's much improvement, high improvement compared with the plain carbon steel. But still with the new material coming, like introducing new material, harder material, and so on. High speed steel also not very well, and then they introduce whatever we call cast cobalt alloy, which is show much some improvement against high speed steel, especially at higher temperature. Later on, carbide, cemented carbide and carbide tool introduced and show much improvement, and so on. Ceramics is introduced as a new material. This is mainly because of new material is coming, aerospace material, advanced material is coming, and HSS become not suitable. Then cast cobalt alloy come, cemented carbide, ceramics, all this material been used to manufacturing tool, mainly to achieve whatever we call good hot hardness. Not hardness, but good hot hardness. I mean, maintain a hardness at elevated temperature. We will start this material, describe or talk about this material one by one, starting from HSS as a first type introduced after plain carbon steel until reach to ceramic and so on, right? One by one. A first material introduced is a high-speed steel. It is a highly alloyed tool steel capable of maintaining hardness at elevated temperature compared with the plain carbon steel. It show much improvement compared with plain carbon steel. And this material, which is a high-speed steel, is suited for manufacturing complicated shape of tools, especially. So this complicated shape of tool can be easily made of high carbon steel or high speed steel material. So what is the high speed steel? What is the high speed steel? Typically high speed steel, we call it HSS. This abbreviation HSS made for high speed steel. High speed steel is a two grade actually. There are a T grade and M grade. T grade is tungsten grade. M grade is molybdenum grade. Molybdenum grade. So tungsten and molybdenum grade. This is a two grade we manufacturing. Tungsten meaning tungsten base, molybdenum meaning molybdenum base alloy. Right, typical alloy is tungsten, chrome, vanadium, and carbon. Let me show you the details. Actually, this is the elemental composition or content of the high-speed steel HSS. Tungsten is made of tungsten, molybdenum, chromium, vanadium, cobalt, and carbon. This is the content, and this is the percentage actually, content percentage for tungsten. For tungsten, in case of T grade and M grade, tungsten T grade 12 to 20% tungsten. In case of T grade, tungsten 12 to 20%. Molybdenum, in case of tungsten, this one, sorry. This is a tungsten content in T grade 12 to 20. In M grade, tungsten is also included. In M grade, which is a molybdenum grade type, tungsten also included, but with only 1.5 to 6%. In molybdenum, when you talk about molybdenum content, in T grade molybdenum, no molybdenum in T grade. In T grade, no molybdenum at all. In T grade, no molybdenum. In molybdenum content in T grade, no molybdenum, but in M grade, from 5 to 10% molybdenum. Chromium 3.75 to 4.5. Vanadium 1 to 5%, cobalt 0 to 12, and carbon, this is a percentage. So what is the item element? Every element we added have a certain functionality. So tungsten increase the hot hardness, improve the abrasion resistance. Molybdenum increase also hardness, improve abrasion resistance. But in somehow there are a difference. Tungsten highly, molybdenum maybe less. Chromium is increasing toughness actually. Chromium, when we add chromium, higher chromium increase the toughness, lower chromium reduce the toughness. So tungsten and molybdenum here is a hard particle. Chromium here, increasing chromium or adding more chromium, this is increases the toughness. Lower chromium meaning toughness is lower. Vanadium combines with the carbon for wear resistance. Cobalt increase hot hardness also. Carbon principal hard element definitely in a carbon steel material. So this kind of element being added together with the plain carbon steel to improve the characteristic of the plain carbon steel. So it's mainly plain carbon steel, and this kind of additive being added will become HSS. Then HSS, as you saw in the figure previously, improves the cutting situation as you saw in the figure, or whatever we described earlier. This is the first material, which is a high-speed steel. Later on, it is improved to cast cobalt alloy. Cast cobalt alloy is introduced later. Cast cobalt alloy is introduced as a new material to manufacturing the tool. Why? For higher hot hardness. For higher hot hardness. As you can see here, at a higher temperature, especially when temperature is very high, for example here, 1200 or more than 1000 degrees Celsius, you can see that cast cobalt alloy show much improvement than the high-speed steel. In cast cobalt alloy, it is introduced 1915, and it is show or better higher hot hardness and higher cutting speed. Definitely higher hot hardness, it means that it allow higher cutting speed. It allow higher cutting speed than HSS, because as you see that, or as we described earlier, when cutting speed increase, temperature significantly increase, tool wear severely also increase. Cast cobalt alloy consists of cobalt main is a cobalt 40 to 50%, chromium and tungsten, and no plain carbon steel anymore. There are no plain carbon steel. We totally change. So cobalt 40 to 50%, chromium 20 to 35%, tungsten from 5 to 20%. This is a cast copper alloy. It is shaped by casting. That's why we call cast copper alloy, shaped by casting. Later carbide is introduced. Later carbide after cast copper alloy. Next generation was the carbide tool. We will describe this one earlier. So this is a cast copper alloy. When you come to cast copper alloy, you can see that cast copper alloy show a higher hot hardness achieved as an advantage over high-speed steel, with resistance definitely of the cast copper alloy better than high-speed steel, but not good as cemented carbide. Cemented carbide is the next generation, show much improvement again is the cast copper alloy. Toughness of the cast copper alloy is definitely less than HSS, toughness lower than. So high-speed steel have a higher toughness, cast copper alloy lower toughness, carbide lower toughness, ceramic is very brittle and lower, much lower toughness. So you can see if you're looking for toughness, then you move in this direction. If you're looking for better toughness or higher toughness, you move in this direction. But if you look for higher hardness and higher wear resistance, then you move in this direction. Then when you talk about a higher toughness, then high-speed steel is the best, but when you talk about the higher hardness, ceramic is the best. Ceramic is a higher hardness, but very low toughness. Low toughness mean very brittle material. And a brittle material means that this kind of material is very brittle, mean it is very fragile, or could be broken easily. So something in between like carbide and cast copper alloy is providing something is reasonable toughness with also very good hardness, as you can see. So hot hardness is between the two material, between HSS and ceramic. Work material include this one can cut steel, non-steel, as well non-metallic material, plastic, graphite, and so on. So this is the cast copper alloy. Next is carbide tool. This is a carbide tool. And carbide tool introduced to allow cutting at a higher and higher, not only temperature but also speed. Because in your CNC is introduced, speed is increased significantly. Previously, you was talking about 5,000 RPM, 6,000 RPM, maximum 10,000 RPM. Now cutting speed increased to 20,000 RPM and 40,000, and later on increased to 50,000 up to 70,000 RPM. 70,000 RPM meaning revolution per minute, meaning spindle rotate at 70,000 70,000 لفة في الدقيقة. So you can see this is very high speed, and you can see that whenever the cutting speed increase, temperature also increase in the cutting zone. Temperature mean when temperature severely increase in the cutting zone, definitely hot hardness required. Then you can see that, so with the time, new material is introduced to adapt with this situation, allowing higher cutting speed in machining operation and so on. Then carbide material is introduced. This is whatever we call carbide. Carbide, we have two grades. We have non-steel grade and steel grade. Non-steel meaning tungsten carbide. W mean tungsten, C meaning carbide, tungsten carbide plus cobalt. So this is non-steel grade, tungsten carbide plus cobalt. This is the first grade. Second grade is also tungsten carbide plus cobalt, but we added titanium carbide and tantalum carbide. Titanium carbide and tantalum carbide are added to tungsten carbide plus cobalt to cut steel grade. So this is a non-steel grade. This is a steel grade, right? So non-steel grade, start first with the non-steel grade. It is tungsten carbide plus cobalt. used for non-ferrous material. Non-steel meaning non-ferrous, gray cast iron and gray cast iron. Property determined by the grain size and cobalt content. As I told you, cobalt content here, cobalt content, tungsten carbide, tungsten and carbide for improving hardness. So this is for higher hardness, higher resistance. Cobalt here, we added cobalt mainly to improve the toughness. To improve the toughness of the material. So hardness here, the properties properly determined by the cobalt content. Higher cobalt content, when we increase the cobalt, higher cobalt content increase toughness. Lower cobalt content definitely will increase the hardness, because when you have a lower cobalt content, meaning higher tungsten carbide, meaning hardness is higher, and also grain size while manufacturing. Grain size meaning that how you manufacturing this one. If you're manufacturing at a high cooling rate, low cooling rate, how you allow grain growth. If you have a bigger grain size, particle grain size, meaning that you increase the toughness. If you have a lower grain size, meaning that you reduce the toughness in the material. This is non-steel grade, and this one mainly for non-ferrous. The other one is a steel grade type. It is thin carbide plus cobalt. This is the original one. This is the one we used previously for non-steel grade. We added in whatever we call titanium carbide and tantalum carbide. When we added these two material, this one become suitable for cutting steel, used for low carbon stainless steel and other steel alloy. These two material added to, and then definitely it is this one replacing some tungsten carbide. Composite increase creator wear resistance wear for cutting steel or for steel cutting. This one mainly to improve the situation in steel cutting. This is second one. Third one is whatever we call, another one we call it is a cemented carbide. Not carbide, but cemented carbide. Cemented carbide, what is the difference? Carbide or cemented carbide, what is the difference? Carbide made by casting. Carbide, which is a tungsten plus cobalt or titanium oxide or tantalum carbide. Whatever we have is made by casting. But cemented carbide, when said cemented, word cemented carbide mean it is made by powder metallurgy. The tool made by powder metallurgy. What is the powder metallurgy? Powder metallurgy, initially you bring material as a powder. You mix the material, all material as a powder, and put in a compaction. Compaction means we apply pressure. When then you apply pressure, it gets shaping, and then you do sintering. Sintering means you put the material, the shaped material, in a furnace. For a while, you get a strength, then you get the material done. Then you manufacturing tool. So tool made by powder metallurgy. In case of tool made by powder metallurgy, they call it cemented carbide. Actually, let me tell you that the tool made by carbide or cemented carbide, the carbide tool made as a cemented carbide show much better, superior properties compared with the one made by casting. To let you know, this is better actually, because here you control the size of the particle in very small scale, like a micro scale. So you manufacturing the material in a micro scale level, then this one can control the properties of the material. This one shows superior properties compared with the material made by casting. Cemented carbide show also two grades. Similar to carbide, we have non-steel grade and also steel grade. So tungsten carbide plus cobalt is a non-steel grade. Same also tungsten carbide plus cobalt plus titanium carbide and tantalum carbide is a steel grade. Very similar to what we discussed before as carbide. So carbide and cemented carbide are almost same, right? When you talk about this one is a non-steel grade, this is a steel grade. So for non-steel grade and steel grade, there are some classes or classification. For non-steel grade, we have classification C1, C2, C3, C4. For steel grade, we have C5, C6, 7, and 8. What is the difference? The difference is a cobalt content. Cobalt content. C1 is high cobalt. Let me write here C1 and C5. C1, let me just put here C1 and C5. C4 and C8. Same level. So C1 and C5 show high. This one show low. Actually, the difference is the cobalt content. C1, C5, high cobalt content. C4 and C8, low cobalt content. 2, 3, 6, 7 are in between. So cobalt content in between. So as we described earlier, this one is a cobalt tungsten. This is one non-steel grade tungsten carbide cobalt. This one tungsten carbide cobalt plus titanium carbide and thallium carbide. So cobalt here, cobalt is here. You can see that cobalt. We have cobalt here and we have cobalt here, right? So you can see that here is high cobalt content. This is the low cobalt content. High cobalt, what is the meaning of high cobalt content? High cobalt content meaning higher toughness. So higher toughness, let me write higher toughness, right? So high cobalt content meaning toughness, tough. Higher toughness, higher cobalt content meaning higher toughness. Low cobalt content meaning what? Low cobalt content meaning hard. Hard. Low cobalt content meaning so higher hardness. If you have low cobalt content meaning higher hardness, high cobalt content meaning higher toughness. So in category 5, 1 and 5 are tough tool. 4 and 8 are hard tool. They are opposite to each other. Hard tool meaning low toughness, tough tool meaning lower hardness. This one is 1 and 5 are suitable for rough cutting. Suitable for rough cutting. 1 and 5. Grade 1 and grade 5 are more suitable in rough cutting. Why? Because in rough cutting, we're removing big amount of material. When we're removing big amount of material, as you know that in rough cutting, when we're removing the feed is big depths of cut, we're providing here big feed and big depths of cut. We're removing big amount of material. The machine is, or the tool is subject to interruption cutting. A lot of impact coming. Boom, 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 boom. A lot of impact coming to the tool. Then the tough tool is more suitable in rough cutting. So we usually try, or we in rough cutting, we try to use the tough tool, meaning higher cobalt content. But in case of low cobalt content and the higher hardness tool, then it's better to use the higher hardness and lower toughness with the whatever we call ultra precision finishing or precision finishing. Precision finishing, actually we use here very low cutting condition, very low feed and very low depths of cut and very high speed. Very high speed and low feed and low depths of cut. The harder tool better. Why? Because temperature, because the speed is very high, very high. When the speed very high, up to maybe 30,000 rpm, 40,000 rpm, then temperature significantly increase. We're looking for here, we would like to have a hot hardness or high hot hardness material. Then better to use a low cobalt content or high hardness or high wear resistance or high hot hardness material in precision finishing. In between general purpose and finishing or high finishing or good finishing and so on. This is a grade of the carbide grade from 1 to 4 in non-steel and 5 to 8 in steel material. Any question? Guys, any question? Okay, no question. I hope it's clear, right? That's it. So move forward. Cemented carbide in general, high compressive strength, high hardness, high hot hardness, good hot hardness, good wear resistance, high thermal conductivity, high elastic modulus stuff is okay. It is less than high speed steel, but it is still reasonable toughness, providing reasonable toughness. Coated carbide. Next, we're going to talk about coated carbide tool. Coated. The word coated here, we coat mean we cover the surface with the other material. Then coated carbide, we coating the tool with a layer. We coating tool with a layer. Like here, you can see that there are a layer. Tool, it could be sometimes creating insert tool. Sometimes tool is solid. We call this one is a solid tool made of the material. This is the insert tool. Insert, you can see that the edge, we manufacturing the cutting edge and we fix in a holder. Then here, this is the cutting edge made of the cutting tool material, or this is the cutting tool material, and we fix with the holder. Actually, this is mainly for hard material. We do this in case of hard material like carbide. Carbide could be solid. Carbide could be solid material like this, or could be also insert made of carbide. So insert here we put in a tough holder like steel, made of steel. So it's combined between the hard and hot hard insert made of hot hard material or hot hardness material, and this one made of tough cores, and you mix between good toughness and hot hardness, or hardness or high hardness and hot hardness. Also carbide is have a reasonable toughness, so solid material can be, so solid tool material could be made of carbide as well. So coated carbide actually is this to we coating carbide with the other material to improve the mechanical properties or hot hardness of the carbide. So cemented carbide insert or solid tool coated with one material like titanium carbide, titanium nitride, or aluminum oxide. Aluminum oxide is ceramics. Ceramics is harder and hot harder material. So we coat a layer on the surface. You can see different color. This different color coming from a layer coated on the surface, a layer coated in the surface. Then a coating layer 2.5 to 13 micron. The coating layer is very less actually, 2.5 to 13 micron, a layer coated on the surface. So it could be titanium carbide, titanium nitride, aluminum oxide. Why we do this? So allowing the cutting edge now, not carbide, but the cutting edge is now is aluminum oxide, for example, and aluminum oxide show better properties and a higher hot hardness, while the core or the material made of tough material, more tough material, because aluminum oxide very hard. Then it's better to coat with the aluminum oxide and keep the tool material as a carbide more tough than aluminum oxide. Aluminum oxide is harder and more brittle material. So coated applied by whatever we call chemical vapor deposition and physical vapor deposition. This way, this is the method. This is a technology we use to do the application of coating to coat the material. Application: cast iron, steel, turning, milling operation, higher speed actually, dynamic force, interruption force. It's better to make a core of tough material and coated with a very hard material like oxide material and so on, right? Cermet is another material being introduced also. This material also provide a good hot hardness. So it's combined of titanium carbide, titanium nitride, and titanium carbonitride. So it's made titanium carbide, titanium nitride, titanium carbonitride. This material is very good actually. We added some nickel and molybdenum as a binder. Nickel and molybdenum being added as a binder. Application for high-speed finishing, semi-finishing steel, stainless steel for cast iron, high speed and lower feed. Definitely higher speed and lower feed because this material become really brittle material, and feed must be reduced. Depth of cut must be reduced. Speed, higher speed is okay because this material is hot hard material. Better finishing achieving, actually not better but excellent finishing could be achieved by cermet material. Later on, ceramic is introduced. Later on, ceramic is introduced. Ceramic material like aluminum oxide. We said that ceramic material oxide, carbide, nitride, generally oxide material. The best is oxide usually. Then ceramic material made of oxide, aluminum oxide material is introduced as ceramic material. This material only manufacturing as an insert, no solid tool as a ceramic. Why no solid tool as a ceramic? Because ceramic is very brittle. Ceramic is very brittle. If you manufacturing tool as a ceramic, as a solid tool made of ceramic, this tool will be broken. This is one. Another one will be very expensive. So usually ceramic made as an insert, only insert, and this insert hold it, fix it on in a holder. This kind of insert being fixed in holders, definitely soft holder. Then now you mix between a hard material and tough material. Holder is tough material. This is because of ceramic is very hard and very brittle and very low toughness material. Actually, this kind of insert made by powder metallurgy, made not by casting but powder metallurgy. So grains, fine grain of aluminum oxide and centered at high pressure and temperature into insert. So insert made by powder application, high speed turning gas. So mainly high speed. When I introduce a harder material, meaning higher wear resistance material, meaning higher hot hardness material, then you must understand this material suitable to be used in a higher temperature, meaning higher cutting speed and lower, definitely lower feed and lower depths of cut. Means that this material is more suitable for use in finishing and precision finishing rather than rough cutting. We avoid using ceramics tool in rough cutting because ceramic is very brittle material. If you try to use, not recommended for rough cutting because it is heavy interrupted. Rough cutting mean heavy interrupted cutting. So this one probably could be broken because it's very brittle material. It is definitely recommended for high speed machining. It means that you can do rough cutting by other tool, and when you come to the finishing and precision finishing, probably ceramic material is better, can withstand very high temperature. In a cutting zone. Right. So this is a ceramic material. After ceramic is also diamond. Diamond is introduced. Diamond. When you say diamond, is the hardest ever material known in the world. Diamond is the hardest ever material known in the world. Very hard material. Diamond like glass, very hard and very brittle. Glass, if you drop, it will be broken. If you have a part of glass and you drop it in the floor, it will be broken. So diamond like glass is very hard and very brittle. Very hot hardness material. This one is worthy to be used in a very high speed cutting. Very high speed cutting. Because this one is very hot hardness material. So here we call it is a synthetic diamond center polycrystalline diamond fabricated by sintering the fine grain, also powder metallurgy. So we get it the powder, the diamond powder, and we do powder metallurgy. We manufacturing to the desired shape of powder metallurgy. And in this case of diamond, we're not manufacturing insert, but tip of insert, not complete insert. So insert could be made of soft material, and we're manufacturing diamond as a tip here, only cutting edge made of diamond. Why? Because diamond, as you know, very expensive. This is one, and also very brittle. So this is another issue. We hold here by welding. There are some welding technique to hold a diamond in a tip as a tip of cutting edge on insert. Also, diamond could be used as a coating material. Diamond could be used as a coating material on, for example, carbide. No way to manufacturing a solid tool of diamond. This is no way. But we use a diamond as a coating material. This is the material here we coat it with the diamond. So material coating or coating diamond on carbide material makes this material superior, can cut higher what? Higher temperature, cut higher speed and higher temperature. So because of the diamond will be the surface or in a contact during the cutting application, diamond cut non-ferrous material and never use diamond in cutting steel. Never use diamond to cut steel. Why? Diamond cut any material, but not steel. Cut ceramic, very hard material, very hard material, but never cut steel. Don't use diamond with steel. Why? What is the reason? Is it because steel hard material? No, not that. Actually, you can cut harder material like ceramic, but steel not steel. Because steel and diamond both are carbon material. And there are a chemical affinity, I mean similarity, chemical similarity in the composition of diamond and steel. Once you cut steel by diamond, because of the chemical affinity, migration, atom migration or atomic migration quickly happen, even at lower temperature between diamond and steel, destroying, damaging the diamond and also steel. So we never use diamond in steel or cutting steel. Another very good material also we can show is cubic boron nitride. Cubic boron nitride is a next to diamond. Next means is excellent, like diamond. Is really wonderful material. Is very similar to the diamond. It is very hard material and hard material and very also brittle material and also very expensive material. Cubic boron nitride is the hardest ever material known after diamond. Cubic boron nitride, and this one very expensive. Also they manufacturing as a tip of insert, similar to diamond, also made by powder metallurgy. So it's being used as you can see here. Also can be used coating carbide. We can also use cubic boron nitride to coating carbide to provide superior cutting edge. So it also being used for coating application. This one can be used for cutting steel or non-steel. Steel can, ceramic can, harder material, softer material. So cubic boron nitride can be used with wide range of material. Tool geometry. When it comes to the tool geometry, I remind you, we have a single point cutting tool, we have a multiple point cutting tool, different type of tool. When it comes to the tool geometry, there are seven element here, cutting edge as we described earlier in the chapter. And this is determines the performance of the tool. Whenever the tool sharp or using sharp tool or new tool, this angle is prepared in exact condition. But later on during cutting the tool weird, this angle will change, and when this angle change, you must resharpening the tool or changing the tool to increase the cutting performance of the tool. This is a tool geometry. Actually, a tool could be solid tool, could be solid tool, or also holder and insert, insert fixed with the holder in two way by welding. We call it brazing, by brazing technique and welding, or can be holded by mechanical way of holding. So we can hold insert in the holder by welding, by brazing, or by mechanical fixation method to hold insert in the tool. Or tool can be made as a solid material, as you can see. This one, for example, HSS Carbide tool can also insert, could be made of carbide, could be made of ceramics, could be made of diamond, could be made of cubic boron nitride. So this is a different type of, if you talk about a single point cutting tool. When you come to the insert have a several shape. Insert have a round shape, square shape, rhombus with 80 degree, as you can see here, hexagonal with 80 degree, triangle, rhombus with 55, rhombus 35 degree, several type of shape of insert. This is actual photo. This is actual photo of the insert, and mostly, as you can see, this is a very common shape in the insert. In this direction, when you move to this direction, strength increase. When you're moving to this direction, ability of cutting increase. So this tool, for example, have a higher ability. This one have a higher strength. Higher tool have a higher strength, and this kind of insert we usually fix it on a holder, and this holder usually soft holder or soft material, made of soft material. So tool usually or insert usually made of harder material like ceramic, diamond, cubic boron nitride, harder material. Tool made of softer material to provide enough toughness, mixing together providing enough toughness. This is the actual photo of the tool insert. Next is a twisted drill. Twisted drill is another type of the tool actually. So you can see that the most common cutting tool is making hole, making hole or creating hole in a workpiece, usually made of high-speed steel. This is the actual photo of high-speed steel, and it could be made of carbide or even cemented carbide or even coated carbide. So it could be any of this material be used to manufacturing the tool. And this is the geometry of the tool, as you can see here, as we described earlier. Actually, this twist drill is creating a hole, as you can see. The mechanism is this one is rotating and feed, and chip usually exit will remove against the direction or opposite direction. So tool feed inside and chip move outside in an opposite direction. This one leading to problem. Problem actually is very, very difficult because when a chip moving in the opposite direction, this one make two problems. The first problem, this is a chip is wrapping between, make a wrapping or friction is high friction due to the wrapping between the outside diameter of the drill and your tool format. And also, if you try to lubricate, it's very difficult because if you try to apply lubrication here, this one will face very difficulty to make lubrication because it will be lubricating against the direction of chip removal. So it is tough operation. It is really very tough operation. It is okay in some condition if you're cutting softer material or if you're drilling not very big dimension, but in case of harder material and so on, different type of tool introduced in a market. We call it is a straight float tool introduced. Straight float tool is this one. This one made of a straight edge, as you can see. It is alternative drill bit with a straight flute being used. It is straight flute drill using indexable cemented carbide. This is the indexable cemented carbide being added here, and the tool made of straight flute. This one provide very good alternative and very good benefit. So drill flute are stronger than a spiral flute drill bit and resist broken when drilling into hard and abrasive materials such as hard steel and rock hard. So it is harder material. This one provide an easier chip removal. So easier chip removal with a tungsten insert here or carbide insert here, and solid tool to provide very good alternative compared with the spiral tool edge. Bit provide free cutting action, as you can see here, making this one stronger and better to be used. And the bit straight flute help can easily chip. I mean, better chip evacuation in horizontal drilling application, as you can see. This is whatever we call is straight flute edge. Alternative drill is whatever we call is a gun drill. This is a gun drill providing also alternative drilling process compared with a spiral drill bit. Actually, time is finished. I have to stop here.